what's at the alpha position? So we're minus 2.3 plus, let's count up alpha substituents first. What's at the alpha position?
An alkyl chain.
Yeah, so there's a butyl group, right? 1, 2, 3, 4 carbons. So that alpha butyl group is worth 9.1. Okay. What else do we have that's alpha to that carbon? Okay. So 2 CO2s is 45.2 in total. Yep. Okay. And those are alpha substituents. And that, this is confusing, that includes each of those two pieces. So we don't have to add the oxygen again twice. Okay. But we do have to take into account that there's also a beta alkyl group, which is plus 9.4. So this was our alpha alkyl. This was our beta alkyl. Okay. We also have a gamma alkyl. Do we have any other gamma stuff that we need to take into account? Yes.
Would you consider the ethyls?
Yes.
Wow.
So that's gamma, and that's gamma. So we actually have 3 gamma alkyl groups, which is a total of minus 7.5 for the 3 gamma alkyls. Okay, and we have 3 delta alkyls, which is minus 3.7 for the 3 delta alkyls. So again, even though the delta numbers are small, if you've got 3 of them, they just have to add up. Okay. Delta alkyl. Okay. Now, our carbon of interest is primary, secondary, tertiary, or quaternary. Tertiary carbon, okay? How many substituents other than hydrogen are on the atoms that are directly bonded to the carbon? 3. Okay. Anybody else have a different perspective? So there's this little footnote here that says, except that CO2R groups, esters, are counted as column 1. Okay? So our carbon of interest is tertiary. Those 2 esters count as 0. So it's really just this group here that counts. Okay? This carbon is attached to 2 carbons. And so we have to add that minus 3.7 number for the steric correction. I screwed up here somewhere. Where was my delta alkyl? This was 0.9, sorry. 3 deltas were worth 0.9. The minus 3.7 is our steric correction. Sorry about that. Reading off my notes. Okay, so let's just summarize all this. Okay. So we've got minus 2.3. We start out with methane, okay, the parent compound. We have an alkyl group, the butyl group. We have a beta alkyl group, the propyl group. We have a gamma alkyl group, the ethyl, and a delta alkyl group, the methyl at the end of the chain. We also have an additional 2 gamma alkyl ethyl groups and an additional 2 gamma delta alkyl methyl groups from the 2 ethyl esters. Okay, so the simple calculation here is basically all of these alkyl groups plus 2 alpha CO2s. Okay, and then it's this steric correction that's tricky. Okay, So the carbon is tertiary, so we're reading off of this row. Okay. The two ester groups count as 0 because of this footnote. Okay. And the other carbon is attached to two other carbons, and so we have to add this minus 3.7 correction. Okay. That gets us to 50.9, which is actually none of the numbers that came back, but lots of you were close. And the actual number is 52. Okay. This is really, really, really complicated, and a measure of how complicated it is this was the typo that's in the earlier version of this book. So even the authors of this actually misinterpreted their own instructions in the footnote here and used the wrong number, and then they corrected it in the subsequent examples of this book. Okay. So it's very complicated and very tedious to do. But there's good news, is that this is exactly the kind of thing that is readily automatable. Okay? So when you draw, those of you who have the full version of ChemDraw, and you draw your molecule in ChemDraw and you hit predict carbons, ChemDraw is very dumb, doesn't do any of this fuzzy logic stuff that MNOVA does, doesn't really know very much about what the molecule actually is, but is really good at working through this additivity table fairly quickly. And so these kinds of additivity calculations are exactly what ChemDraw is doing, and it even, I'm pretty sure it even knows how to read off this steric correction correctly.
Is that new ChemDraw has the prediction?
So all the versions of every year of ChemDraw since the mid 2000s, if you buy the Ultra version of ChemDraw, has the NMR prediction built into it.
Ultra means the one like we don't get from.
Yeah, but our site license is for the STD version of ChemDraw, which does not include the NMR calculation.
Okay.
So that's the difference. It's not a very good. I'll show you when we get together next time. I've given you some calculations to do, and I'll show you the ChemDraw output for those calculations as well. And you'll see that it's not particularly accurate, but it's not more or less accurate than doing it this way. In fact, it's using a very, very similar additivity table. Mm-hmm. It's not exactly the same as the additivity table that you have here, but it's similar. And that's basically what it's doing. And it's a fast process, because even though this is tedious for you to do, it's very fast for even a very low budget computer to do. Okay, good. Questions about that? Okay. So, on your assignment, I've asked you to calculate 2 carbon shifts, one for each of the molecules that I've given you, and then you'll be able to look up the authentic spectra for those as well and see how close you are or far away. Okay, more additivity tables for carbon chemical shifts in aromatic rings. I think you get the idea by now. You start with the parent system, which is the carbon in benzene in chloroform, comes in at 128.5 parts per million. And then you take into account all of the substituents that are attached at the ipso position to the carbon you're interested in, the ortho, meta, or para position to the carbon that you're interested in. Again, this is going to be very accurate for monosubstituted aromatics, pretty accurate for disubstituted aromatics, less accurate for trisubstituted aromatics, and so on and so forth. Okay? But you can get a reasonable estimate of what your expected carbon chemical shift is for any fairly simple aromatic compound. I won't even work through an example there because I think you get the idea by now. For simple alkenes, you start with the carbon chemical shift for ethylene. You add on the substituents that you have either at the carbon of interest or next door to the carbon of interest. And there's a simple steric correction that just counts up basically how many different geminal substituents you have, which are going to distort the bonds somewhat, just because if you've got 2 substituents on one carbon of an sp2 center, they're going to start to move the bonds a little bit, because otherwise they would bump into each other. So the steric correction here is fairly simple to apply, and this calculation is very, very easy to do. What's the big picture? You've all seen images that look like this, I think, from your second year spectroscopy course. I don't know how useful these are, but sometimes it's useful to keep in mind, without even having to calculate anything,